Looking at sort of an illustration here, you can kind of see the ellipse nature of the orbits of the planets and with their eccentricities. But again, let me point out that for our planets in our solar system, the eccentricities are actually pretty close to zero for the most part. The highest value is 0.25 for Pluto and Mercury at a 0.206. Looking at this illustration, here's an ellipse with an eccentricity of 0.23. You just glance at that. If you weren't told it's not a circle, you'd probably say it was a circle. So for the most part, these aren't really strong ellipses for planets in our solar system. But again, this applies to comets and asteroids and other things as well, which would have more elliptical things. Okay, so that's what it looks like. Kepler's second law then is the law of areas. And it says a line connecting a planet to the sun sweeps out equal areas in equal times. What does that mean? Well, this applet here will allow us to look at this idea of sweeping out equal areas in equal times as we've got this planet moving around a sun here. This one's actually a perfect circle, saying that, okay, over a certain amount of time it's just, shading, these equal areas in equal times, as you see. Okay, so each region, black and yellow, is same area for the same amount of time. Now, what we're going to do here is we're going to increase the eccentricity because it's not really surprising with the circle. So, we'll warp this. Let's go to this value. So here we're still going to be moving equal areas in equal times. Now, what's that red vector indicating? That's indicating the velocity of the planet. Okay, so that's our velocity vector. So as you see, to be able to have equal areas in equal times, it means when the planet is close to the sun, it has to move much, much quicker than when it's farther from the sun so that it can sweep out this equal area for the same amount of time. Okay, so we have to speed up in those cases. Moving to some values in here, same idea. So a little less dramatic than the last example, but it's going a little faster here and then a little slower when it gets further from the sun. Kepler's third law of planetary motion is that the square of the period, in other words, how much time it takes for the planet to go around the sun once, so the square of that is proportional to the cube of the semi-major axis of the orbit. Okay, well, what are we talking about there? The semi-major axis of the orbit, if you recall, the semi-major axis for an ellipse is just, half of that distance across the major axis, across the center there. This is really a data analysis thing, just doing a best fit kind of data curve here. In this particular example, they were taking the square of the orbital periods. Okay, so this is the number of years squared for each planet to go around the sun. Okay, in Earth years, and the cube of the semi-major axis. And by plotting those two values, you end up getting a straight line. Okay, which means you get the proportionality between, as I said, the period squared, indicating the t there, t squared, and a cubed is that length of the semi-major axis cubed. And then the slope of this line is that proportionality constant. Turns out to be 4 pi squared over gm, where g is the universal gravitation constant, and m is the mass, I think, of the planet. Oops, sorry, I meant m is the mass of the sun, not the planet. And, we could talk about this orbital mechanics then also applying for planets going around other stars, using those masses of those stars. So that's what Kepler's laws are. Now we're going to go into proving some of this. Again, Kepler did this all by observation. It's called the scientific laws because it's what he noticed. It seemed to always be true. It's not a proof.